Okay, let's get started. Are you ready to start? Thank you. Okay, let's do some examples from the homework. That cause a little more difficulty. See number 5. This one. Let's look at number 2. Okay, this one. Okay, so I think we look at this and we say, what can we do with this? So we're thinking, it's looking 8 sine squared plus 9 sine x. Well, that kind of has a polynomial feel to it, right? But it's got the sine in it. So how can we get rid of the sine? We can make u equal to sine x. And then du equals cosine x dx. Okay, and before we start changing this around and solving for dx, just kind of notice what happened there. Look, what does du equal to? Cosine x dx. So we could solve for dx and kind of work this around, but if we just notice, look, cosine x dx is equal to du, right? What do you have in this? Cosine x dx. You see it right there. That's du. We just found that. So rather than solve for dx and then have this cosine, in which it would work, you know, the cosine. But if you tried to change the cosine x into u, then you'd be down a rabbit trail that wouldn't be good. So the easiest thing to do here is just you get this cosine x dx and just recognize, oh, there it is right there, cosine x dx, and that's equal to du. So then what you have is 1 over 8u squared plus 9u times du. So now we have to go through our techniques and figure out what technique can we use to solve this. Well, we certainly can't undo the chain rule. That doesn't work here. Partial fractions. Okay, so in order for partial fractions to work, what has to be true about that denominator? It has to be factorable. And it is. We can factor out u. And then that should be a pretty straightforward partial fractions problem. We're going to have a over u plus b over 8u plus 9 is equal to that thing. And we got to figure out what a and b are so that the numerator is 1 when we add those together. So do you want me to finish it, or that's pretty easy? Finish it, or do a different one? Let's just finish it. Okay, so your numerator is going to be that 8 times au plus 9, and that's going to equal 1. So we're going to have 8a plus b. Those are our coefficients with a u. That's going to equal 0, because those are my u's. And then 9a equals 1. So yeah, so the 8au and bu, that's going to, we have 0u over here. And then 9a is my only constant term, so that has to equal 1. So then a equals a ninth, and b equals negative 8 ninths. Check my math. Is it right? So then my integral will be, so this integral is the same as integral of 1/9 over u du plus negative 8 ninths over 8u plus 9 du. So now we're ready to do the antiderivative. The whole point of switching this into u is so we get an antiderivative that we can do once once we apply the partial fractions technique, we've got easy, so we've got two natural log antiderivatives, and then we're going to change those back into x after we take the antiderivative. So 1/9 natural log of u, which is, I'll do this, can I antiderivative and substitute back in one step? Because I'm running out of room. Is that right? Because it would be 1/9 ln of u, and u equals sine x. And then it's going to be, what? We're going to need another 1/8. This is being minus 8/9 times 1/8 times natural log of 8 sine x plus 9. Sorry, I did not. I'll write it up here. I'm going to put it in the box. How about that? So we're ready to put the answer in. 1/9 times natural log of sine x minus so 1/9 is 8. I'll just do it out. 8/9 times 1/9, 1/8. Sorry. They do. I'm just going to write that out. Natural log of 8 sine x plus 9. And now this problem gave us the plus c. So you have to be on the lookout for that, right? Where these indefinite integrals, it represents all antiderivatives or all quantity functions that have that given rate function. So you have to, for these indefinite integrals, you have to have plus c. Some of the, as we've seen all semester, some of the Weber problems have the plus c after the box. Some don't, so you have to put the plus c in your answer box. Here's one where they put the plus c to the right, so we don't have to put it in the answer box. Okay, do you agree with my answer, those who are keyed in? Let's see if it's right. Okay, great. Questions on this example, please? Because of the, if this would be 8u plus 9, so when you do the, yeah, so when you do the derivative, you'd have an extra times 8. So I'm including the 1/8. It's like a mini undoing the chain rule. Yeah. Other questions on this one? Okay. Next problem is, we'll do number 3. So for this one, again, we're seeing this kind of quadratic form in the denominator, and so it's just a pure quadratic. We want u to be what? E to the x. And so that means that du equals e to the x dx. And so for this one, I don't really have that e to the x dx anywhere, so I'm going to actually solve for dx. Dx equals du over e to the x, which is u. So then this thing becomes negative 17u minus 21 over u squared plus 4u plus 3 times du over u. So this one was similar to what I did in class, but it's different. So yes, we do similar exercises to help you do them, but you still have to do the math right if it's slightly different. You can't force it to be like the example you've seen before. So what's happening here? I think before there was just like, in my example in class, maybe there was just a single u up top here, or a u squared or something, where this u canceled out with something, but this u isn't canceling out with anything now. Okay, so this u is part of our denominator. So yes, use similar examples, but you still got to do the math right. Okay, so minus 17u minus 21 over, so this factors as what, u plus 3, u plus 1, but times u, right? So this is now you have actually 3 factors in the denominator, du, because that u doesn't cancel out with anything in the numerator. So it gets multiplied into the denominator. So we actually get 3 partial fractions. When we decompose this, it's going to be a over u plus 3 plus b over u plus 1 plus c over u. I'm not going to do this one. But then we need that thing to equal this. So I'm guessing that's where we ran into a lot of difficulty. If you were trying to make this just like the one in class, well, it's similar to the one in class, but not just like it. This u actually this time becomes part of our denominator and gives us three partial fractions as the decomposition of this one fraction. Yeah?
When I was doing it, I tried to move the u outside the integral. Why can't you
No,
do that?
because it's part of the function. It's not a constant. Yeah, I mean, it's the variable. It's the variable for which we're integrating. So you can only move constants outside. So this is our variable u. Other questions? So that one's just longer. It's still it's on the easier side, just more tedious. Yeah.
On the web work, I had a hard time deciding what was going to be my u.
Uh-huh.
It's like multiple trig identities.
Okay.
It's like cosine.
Uh-huh.
It's like a strategy.
So it's kind of just some trial and error. So you try it until you try something and see what the resulting integral is. And if you can get into something that's a technique we've seen before, then you're good. If it's not, then there was another option for you. Try that other option. So it's kind of a combination of trial and error and then experience. Like so, once you've done a lot of them, you get better at knowing what you should be. But there is a trial and error aspect to it. Yeah. Again, so maybe going off that question, looking at the last one here. So, do you see what the obvious choice for you is here? No. So what I see here from experience is that look, I've got sine x dx, and I've got cosine squared, and that's indicating that u should be plain cosine x, because then du is negative sine x dx. And that's essentially right there. So this in what I've circled now is the opposite of du. And then my denominator will be 1 plus u squared. So I'm looking for things like that. I'm looking for what's going to really make this thing get really simple. What value of u is going to make this really simple? So then I get negative 3 over 1 plus u squared du. And so that's one we just recognized, right? Negative 3 arctan u. And then our u is cosine x. Question? Is there a question? Yeah.
For this one, because you get the negative sign,
Yeah.
it's positive in the original. Are you allowed to put the negative on the outside of the integral?
Yeah, negative is like negative 1. That's a constant. So if you have an inside or outside, you just get a negative. After the antiderivative, you just have a negative.
Okay.
Yeah, but constants and integrals, you can move constants out, and that would just be a constant of negative 1.
Okay.
Yeah, sure. Yeah,
How did the negative get there for du?
because du is negative sine x dx. So here I just have positive sine x dx. So that's equals the opposite of du. Right? Sine x dx is equal to the opposite of du. If du is the opposite of that, then the opposite of du is sine x dx. Because I don't have the negative here in the sine x dx, but I have it here. So then I just throw the negative in there. Okay, in your book, there's what's called a table of integrals. 3 pages in the back, like in the appendix. There's an appendix in your book, table of integrals. So the first page, basic integrals, ones that shouldn't be in a table because we just know them, okay? But then some more forms here. trig integrals. So these are just basically solved integrals. So then they get more complicated as we go. So there's reduction formulas, and then we have these forms, and this is on page 2, integrals involving a squared minus x squared. So all these different versions of integrals that involve a constant squared minus x squared. And then x squared minus a squared. And then page 3, integrals involving a squared plus x squared. Integrals involving ax plus or minus b. So these are basically general forms of all these different general forms solved. So let me show you how you use this. So for example, if we have the problem this problem right here. 1 over x squared times 4x squared minus 7. Okay, so we think through our techniques. Is it undoing the chain rule? No. Is it trig? No. Is it partial fractions? No, because of the square root. Okay, so we think through. Is it undoing the product rule? Doubtful, okay? If it were undoing the product rule, it would be ugly, and we'd want to avoid that, right? Definitely not one of our common forms for undoing the product rule. So we think, okay, is there a substitution we could do? And so we could try, maybe we could try u equals 4x squared minus 7. All right, well then what is x squared? Then x squared is u plus 7 all over 4. But then what is dx? So dx is not simple here. So this isn't really helping that much. Dx is not simple. X squared is this ratio, and then we'd have the square root of u. So we might be able to keep working the algebra to make that work, but it's not looking straightforward. So now we think about, okay, so is this similar to like one of these forms I just showed you in the table? So we're thinking like maybe there's a table form that we could use. So we notice that we have 4x squared minus 7. Okay, and then did you notice the one category that was kind of like that? Forms involving x. So there's forms, one of the things I had showed you was forms involving x squared minus a squared. Well, so that's something close, but this is 4x squared. So here's where we do a change of variables to make it look like the table. So we're going to do a change in variables to make that what's underneath that integral, instead of being a constant times x squared minus 7, we want it to just look like something squared minus 7. Okay? So that means we want 4x squared. So in the end, we would want u squared to be 4x squared. Right? Because then we'd have u squared minus 7. And that's promising for using the table, because it has that form of what? U squared minus a squared. So if u squared equals 4x squared, then what is u? 2x, right? So by making u equal to 2x, it will make this u squared, and it will match that type of form in the table of something, a variable squared minus a squared. So now we just need to rewrite this thing in terms of u. So we need to know what x squared is. What is x squared? Well, we can get that from here. X squared is u squared over 4. Okay, and then what would dx be? So we can get dx from here. X is u over 2. And so dx would be 1/2 du, right? So now we're ready to set this thing up, change our variable into u. We've got all the pieces we need to change this to u. So this thing would be the same as integral 1 over, what did we say x squared was? U squared over 4. And then we know our 4x squared is just our u squared. minus 7. And then dx is 1/2 du. Okay, let's simplify this. So dividing by 4 in the denominator is like multiplying by 4, right? So this is like multiplying the whole thing by 4, and this is dividing it by 2. So we can just make that 2 in the numerator. So this would be a 4 in the numerator, and this would be 2 in the denominator. 4 over 2 is 2. So then u squared So now, can we go to the table and find one? Because we don't have a technique for this. We don't really have a technique for this. It doesn't really follow any of the ones that we've learned. But the whole point of what we've done, this change of variables, is we got this to look like hopefully one in the table. Okay, so we go to the table.
Wait, wouldn't you change 7 to base squared?
Yeah, so just noting that 7 is going to be like
Squared.
so noting that it's going to be minus, if we were looking for forms of a form of variable squared minus a constant squared, then that 7 will be like a squared. Yeah, so we'll just that's no problem, right? Because then it'll just be the square root of 7 squared. Okay, so let's look in that table here. And I don't want to take away the writing, so maybe I'll just move that to a different. Okay, there we go. So we were looking for what? Forms involving x squared minus constant squared. So here they are. 68 through 75. Make it a little bigger. 68 through 75 are those. So we got to get the one that matches what we had. We also had that u squared in the denominator. So now what's a little confusing about this is they've made this table in terms of x. Usually integrals are given in terms of x. We're going to change the variable to something else, but then they give us the table in terms of x. So you got to kind of pretend all these x's are u's, okay? And then it'll help. Because we've changed, ours was given an x, we changed it into u's, so now we've got to pretend that these x's are u's. So which one of these, 68 through 75, matches the form that we got? Let me write that down again. Do you see that it's 70? Because we had u squared and then u squared minus a squared. So here it tells us exactly what the answer is. It's this right here. So write this. So write down 70. I can't write with my pen on this desktop. So you're going to just write down table formula 70, and then write this out right here. Write this out, that if it's this general form right here, your antiderivative is this. So yeah, go ahead in your notes and write out table formula number 70 and write that whole thing out. Because my pen doesn't work on this desktop. Okay, got it? So now we're going to go back to our problem here, and we're going to apply that. So if that's the antiderivative, we're going to apply it to our integral. Here we go. Maybe. Let's try this. There we go. Okay, so what did you find? So it's going to be 2 times, what was it, square root of, was it x squared minus a squared? Yeah. So we're going to just write that down. U squared minus 7 over a squared. A squared for us is just 7, and our x is u. We'll do the plus c at the very end. So is this the right application of that table formula that we just had? Does that do it? Okay. Well, but now we've got to switch our u back into x. So what was our u again?
2x.
Our u was 2x. Our u squared was 4x squared. So now that's equal to 2 times 4x squared minus 7 all over 14x. So then we can simplify 2 over 14 as 7. So we get the square root of 4x squared minus 7 all over 7x plus c.
We're gonna give this a table on the exam.
Yeah, so if you use the whole point of doing it by a table technique is that you don't memorize it, you have the table, you use the table. So I'm not asking you to memorize any of the table formulas. If you're going to apply the table technique, then you have to have a table, or part of at least part of the table that you're going to need. Okay, does that example make sense? Okay, so let's take a look. Let's look for one more example in the web work. The ones we did. Issue. How about this one? So this is negative 5 over square root of x squared plus 16. What's that?
You don't even use the substitution there.
What could you do for this? Oh yes, exactly. So it's just ready to use the table. So for this one, you're just gonna look for the right form. So let's just did you write that down? And then also write down. Let's see. Okay, so do we have this one written down? So here's forms involving a squared minus x squared minus a squared, and then there's a squared plus x squared. What? Oh, sorry.
7.
There we go. Everyone look, which one are we going to use for that? There's some people are saying 77. Does that match the one that we were given? It was what, negative 5 over x squared plus 16? Okay? Boom. So this one you don't even need to change the variables in the first place because it is exactly in that form. We just have a negative 5. And the value of a is 4, but you don't even need a, you just need a squared, so you don't never really need a anyway. So we're just going to write down. It's going to be negative 5 times natural log x plus square root of 16 plus x squared. Order doesn't matter inside there. Plus c. Okay, so there may be exceptions, but for us, for our sake, we're going to be using these tables mostly So use table mostly for forms involving a squared plus x squared, a squared minus x squared, and x squared minus a squared. So those will be the most common ones we'll use it for. But that's not to say that there might be some other possibilities like ax plus or minus b or something like that. So that's 1, then 2, x squared minus a squared, and 3, a squared minus x squared. Normally, ones that involve these, with a few exceptions, there's some basic inverse trig that we know, like 1 over 1 plus x squared. We know that one. That doesn't need a table. Square root of 1 over 1 minus x squared, or 1 over the square root of 1 minus x squared is our arc sine. But when it gets a little more complicated and involves one of these three forms, that's going to be our cue to use a table. Anybody have a question? Okay, so here's the game plan. We'll have web work on this table integrals. It'll be pretty short, and I'm going to post. We're going to start working on the idea of not. So now that we've finished all the techniques, there's this added skill that you have to have of come to any integral and know which technique to apply. So as we've gone through the different types, you've never had to do that really, a little bit. So I'm gonna post part of the review for the exam, which is a list of 20 or 25 integrals, and they're all mixed together. Okay, and so in recitation, you're going to start working on that. The exam is a week from Friday, and remember, it's going to take longer than the class period. We have this room reserved on Friday, so if you've got a conflict right after class, please let me know. But we will go longer than, we'll go after 3 o'clock to finish the exam, a week from Friday. And we'll start, like I said, I'll start posting some review materials, especially the integrals, the integral techniques.